that we're going to have a panel where we'll have a bunch of the recent speakers from the last 2 days discuss topics. That panel will be open for questions. So if there's any remaining questions for some of our speakers, feel free to chime in. We're going to start this afternoon with a talk from Jason Lee. I forgot the title of the talk, but he's going to talk about some of the recent work he's been doing on the theory of large language models. So thanks so much for coming.
Yeah, thank you, Sasha. Thanks for the invitation. So my talk is two halves. The first part is about scaling laws when using SGD as a learner. The second part will be about learning compositional functions with transformers. The two halves are completely separate, so if you get lost, it's all good. You can just wake up for the second half. This first one is work with my students, Yunwei, Yishan, Denny, he's a postdoc at Flatiron and NYU, and myself. Okay, the first part of the talk is about trying to understand how neural scaling laws arise. I just want to remind everyone what scaling laws are. I'm thinking of the very original form of them about training a model size or data size and model size from the Kaplan paper or the Chinchilla paper, not test time scaling laws. So they basically found in these papers that scaling laws have kind of the form of you have one parameter, which is the number of training points, or equivalently the number of SGD steps. We're usually thinking about online SGD here. So the number of data points is equal to the number of steps. And the second parameter is the model size. And then you have some offset for the Bayes error, which is this C, which is the lowest possible, even if you had a infinitely large model trained for infinite time and assuming it gets the global minima. And they found curves like this where you can just vary the model size and the training time, and then you take the Pareto frontier, you fit sort of the Pareto frontier. And then you'll get curves. This one is for number data points, where you'll get curves like you find that the loss is proportional to this compute to the power of minus 0.05, some exponent. The amazing thing is that these plots are accurate over several orders of magnitude. This one roughly 10 to the minus 7 all the way up to here. And they have the ability to extrapolate. They're quite predictive, and people use them to tell, should I collect more data or should I build a bigger model, and how to trade off these. On the other hand, another term that's come up a lot recently is emergence. Emergence is essentially the observation that if you have either small models or small amounts of data, you basically cannot learn something. And then suddenly, when your model size or training time crosses some threshold, the ability, you can sharply learn, your accuracy jumps up. So you can think it's like roughly 0 or the random guessing. And then there's some threshold. In this one, 10 to the 22. Where like suddenly you can start learning, and same here for a different skill. So these two things are like very different. This one, the loss curve is smoothly decreasing, right? Like in a very predictable way. Like I can tell you, if the scaling law holds, if you increase your data by a factor of 2, what will happen? But here it's very unpredictable. Like here it's just, it looks like it's going to be, if I fit a line here, it looks like it stays at 0, but then suddenly the ability emerges. So two very different pictures. So we kind of want to reconcile and find a model that exhibits both emergent behavior by acquiring skills, and will have a nice, smooth power law decay in the cumulative loss. So people have proposed models that have these properties. This additive model proposed by a paper led by Max Tegmark, basically they said that imagine that it wasn't a single loss function. It was just a bunch of different loss functions added up. And each one had a different model. This is not how models are trained in practice, but just for the purpose of their thought experiment, this is what they're doing. And then each loss is emergent, meaning like at a different time, the loss will transition from 1 to 0, or 0 to 1, let's say, depending on which way you go. Or here is from 1 to 0. And then every loss curve has a different time. So here's the emergent time for the first loss, the second loss, the third, and so forth. And then if you add together all of these separate curves, again, it's just taking sort of like this, this Pareto frontier kind of thing, you'll get back a nice smooth power law. Okay, so this kind of indicates a possible mechanism where you have a bunch of basically staircases. These emergent losses look like staircases. And you add up like these step functions, and these step functions, sort of like a Riemann integral, can integrate to a nice smooth decreasing function. And this happens if you just have a bunch of different losses for some reason you're adding together with separate models you're adding together. So our goal was to look for models where you have a single loss function, such as the pre-training loss, and a single model that will exhibit this behavior. The loss, if you zoom in, it'll have this microscopic behavior of like a bunch of little staircases where each skill is emerging. And to learn the full function, you need to learn lots of different skills. So then when you add together your ability to learn all the skills, it'll result in this. If you look only at the cumulative loss, you'll see only this nice smooth curve. But if you zoom in microscopically, you'll see these step functions. And we do this using a very simple shallow neural net, which is kind of the limit of our ability to analyze. Yes?
Backing up slightly, do you have like a strong stance on whether emergence is like the appropriate way to think about some of these phenomena, or whether it's kind of misleading to think about it that way because of the metrics and so on?
I'm not very certain, but I find the story compelling that the pre-training loss involves a sum of many different skills. And then the learning of each skill is possibly has a very sharp transition, but then somehow the integral of these result in a nice smooth curve. At least from a mathematical standpoint, I find this very elegant. I don't take any, I'm not sure in practice how you can decompose it into these various skills or something. I wanted to first introduce to you the simplest model in the world that has emergence. For the theorists, this might be very familiar. It's a simple single index model or a single neuron. You have some activation. Think of the activation like some monomial is the simplest case. Like it just raises the argument inside to the second power or the fourth power. It doesn't really matter. But something nonlinear. Basically what you want to do is you want to identify the direction theta in the high dimensions. So you have a lot of possible directions. And once you identify the direction theta, the loss will drop very, very quickly. In the beginning, there's a very long phase that will, what you can kind of imagine is you need once you have some non-zero correlation with theta, then you just have to grow the parameter, and then loss will decrease very quickly. But until you find it, the loss is always at zero. Or sorry, it's always at 1, the baseline of random guessing. So how long this takes, you can characterize this using the Hermite expansion of this. So like I said, it's convenient to think of this as a Hermite polynomial or monomial if you like. This is not very important, but there's basically some exponent that characterizes how long these plateaus are. And it's basically how much information the gradient at initialization has information on theta. And that causes a very, very long plateau. There's some algebra here. But basically, what happens is in the beginning, you have very, very small correlation, 1 over d to the j over 2. Think of j as like 5. So it's like 1 over d to the 2.5. Some tiny number of d is 100. Then basically, the length of this plateau has been characterized in previous work is of d to the power of k. Technically, to be precise, it's exactly d to the k minus 1. But regardless, as long as this k is bigger than or equal to 2, it'll be very long, or bigger than or equal to 3, it's going to be a very, very long phase, a large polynomial in the dimension, and then after that, it takes very few steps, order of 1 steps for the loss to decrease. So kind of in the emergence picture, that's the length of this to this, is a function of d and the signal strength. Okay, so for this toy model, we understand very well both the emergent learning curve. Is that the loss will stay at 1 at random guess for length d to the k minus 1. in which it sharply starts decreasing, where the correlation grows from 0 to 1 very, very quickly, and thus the loss goes from 1 to 0 in essentially log d step. But I'll just use theta tilde of 1. So basically, you need to escape this little region. Once you escape it, you shoot up here almost immediately. OK. So this model exhibits emergence. But now we want a model with multiple skills. So we're going to do the obvious thing. We're going to learn a teacher that's a sum of many single neuron models. So it's a two-layer neural net. The thetas need to be orthogonal or nearly orthogonal. So there's less oh, sorry, yes. No, there's tiny signal. The signal is of size, it's not a random walk, which is why it's not exponential in D. The signal is of this size. Your gradients point in the correct direction, but just of tiny magnitude. Their expectation is 1 over D to the k minus 1 over 2 plus noise. So as long as it's not 0, you'll take 1 over that time to escape, roughly speaking. 1 over that squared, maybe. Because this is like correlation and not square correlation. But yeah.
Can you just reiterate the introduction here? Like, what's the setting? Like, what's the hypothesis space we're looking over, and what's the assumption?
Yeah, sorry. Aside of this single index model, the teacher is a single neuron. The learner is a single neuron. Everything is well specified. And none of this is new. This is all work by Ben Arus and his former students.
You're just learning a single weight vector.
You're learning a single weight vector, a single neuron, yeah, or single index model. And the only thing I wanted to point out is this is a model that has this sort of phase transition, sharp phase transition behavior. Any questions about this toy model? So moving on to the model I actually want to study. The model I actually want to study is a little bit richer. It's going to be the sum of p different neurons. It's a two-layer network of width p, where the thetas are orthonormal or sufficiently incoherent. Again, we're going to assume k is bigger than 2. When k is equal to 1 or 2 are corner cases in this case. They don't have emergence. We're going to vary the size of these APs. These APs exactly correspond to the height here. Like this is A1, it's the biggest, A2 is the second biggest, and so forth. It's exactly the height of each of these curves. Okay, so now we have a single teacher or labeler, and the learner is going to look similar, not exactly the same. I should mention, Okay. We're going to think of P as very large, which is somewhat unusual for this area of this line of work. Is we're going to assume that this is some like D to the 0.1. Usually people treat the width as a very small parameter, but here we want really large width to get the smooth curve at the end. And the condition number will be important. Usually people assume constant condition number for technical reasons. In our case, we necessarily need the condition number to be large because we eventually want to study the case of when the skills are weighted by power law distributions. And we're going to do just regular pure online SGD without altering the training algorithm, which potentially alters the scaling law. Okay, so basically we need two things. We need to characterize the emergence time for learning each individual theta p. They'll emerge at different times, and we need to characterize each one very sharply. And finally, in a sense, integrate that result, these emergence times to get a scaling law. That's basically the two things we need to do. The learner is similar. For convenience, I'm going to parameterize it as two homogeneous. It'll be norm W squared and then W normalized. The reason for this parameterization is that if the model were a ReLU and you train the output layers like column A and the inner layer W's, if you train them with gradient flow, it's equivalent to training this model. Because what happens is the A's always stay positive and it's too homogeneous. You can never cross 0. So the signs will never change. So this model has the same training dynamics as a ReLU 2 layers. And it's sort of easier just to track one group of parameters. OK. So now we're going to do simple online SGD. Every time online SGD is I draw a single sample. It's fresh, unseen, take a step, and throw it away. OK. No reuse of samples. So training time is equal to sample size in this model, sample complexity in this algorithm. OK, the first result is purely about optimization, nothing about scaling laws here yet. It says, oh, and sorry, I forgot to say that, I forgot to say something important, I think. P bar is another parameter because we also want to capture the width scaling. So P bar is basically, we're going to say, declare that we're going to choose M roughly as P bar log P bar. And that's basically, we're not, so our model is under-parameterized, unlike most of existing work in deep learning theory. Is you always train over-parameterized models because it makes the optimization easier. But for scaling law with respect to model size, it makes no sense to be over-parameterized because then your approximation error is 0. So you have to look at under-parameterized models, which means that you declare I want to learn as well as this model as if I had P bar neurons, where P bar is something very small potentially. And then you vary P bar, and then that gets you the approximation aspect of the scaling law. So we're always going to choose M as P bar log P bar. That's the size of our learner. And our goal is to do as well as the best model using P bar neurons. So it's under-parameterized. So for any index less than this P bar, sorry, I have too many P's. Big P is the size of the teacher. P bar is roughly M, how well we want to do. And P is any neuron before P bar. So all of these, we hope we can learn. So then we will learn theta P at this time. This time is proportional to 1 over A, P, the same quantity as in the previous D to some power of K, and 1 over the learning rate, step size eta. OK, so this is the time at which a single neuron is learned. And this is sharp up to like 1 plus little o of 1, actually. So it's extremely tight. It's not even up to, it needs to be tighter than constants. It's tight up to 0.99 and 1.01 in a multiplicative sense. Otherwise, you won't be able to get the scaling law at the end. Because what happens is if it's only tight up to big O, then the order of things being learned will switch. And some funny things can happen. So basically, so roughly speaking, all the neurons up to size M, or P bar, will be learned at this sample and time. So more precisely, you can state a simple corollary is if the learner were the same size as the teacher, then this is the total time and samples you would need. OK, so no scaling law here. This is just saying it's learnable. And we can characterize the time in a pretty sharp fashion. OK. Comparing to why prior works weren't able to do this is they frequently paid exponential in the condition number. The condition number in our setting is proportional to P, so it would be exponential in P, which is not good. Or they require changing the algorithm. For example, they optimize over manifolds of like orthogonal matrices. It's a quite different algorithm, and a different algorithm would change the scaling exponents. OK. So we can now special case this result to a scaling law. Yes. Oh, yeah, sorry.
Can you comment on your assumptions on the input data?
X is Gaussian, yeah.
Why do you assume that covariance is identity? Like what
good question. Yeah, good question. So the first thing, if the activation is homogeneous, it doesn't matter if it's identity or not. If the activation is not homogeneous, you cannot, as far as I know, even this result of Benarus, I'm not sure it's true for regular SGD. You can do a projected SGD where if you knew the covariance, you like project with respect to that norm. And that would work. That would look exactly the same. And everything I'm saying would be true. But you would have to use that algorithm. Yeah, basically, yeah. But if you want to use vanilla SGD, you either need to commit to a homogeneous activation or assume it's isotropic. Yeah. Any other questions? where was I? Okay. So what happens is that, let's say, now we're going to add some assumption on the size of each skill, like how important each skill is. And we're going to assume this is power law distributed. So it has strength proportional to p to the minus beta. Beta bigger than half is the interesting case. When beta is like less than half, you don't get the same shape. And this is a shape that matches the Chinchilla and Kaplan papers. Basically, so again, this is just restating the teeth task. The teeth task is learned at this time. And the population square error will have a power law decay where this is the width scaling exponent. It's the model to 1 minus 2 beta. 2 beta is bigger than 1, so you should think it's something going to 0 with m. And this is something going to 0. And these are the exponents, 1 minus 2 beta over beta. And the other one's 1 minus 2 beta. What else did I want to say? The proof or intuition is quite easy. Once you've characterized the emergence time, the loss, it turns out, you can write down in a very clean form. You can write the loss exactly like as just whether it's small, the current number of steps you're at is smaller than the emergence time TP or bigger. If it's smaller, you incur error a squared. If it's bigger, the error is 0. So it's exactly at this time TP you're learned, or plus minus little o of 1s. So and then the error up to when you've learned only the pth neuron. Yeah, question. Sorry. Yeah, sorry.
So the asymptotics you make n go to infinity, d go to infinity.
All of the errors are 1 over d to something.
Oh, I see.
All of the errors are 1 over d to something. Yeah. Yeah. Like in this Riemann integral. Yeah. Yeah, because p is also in terms of d. Like p, you should think of like d to the 0.1 or something. Yeah, so everything is like going to infinity with d. And then when d goes infinity, n also has to be infinite, and t.
But proportionally, right?
But not in the linear proportion.
Okay.
Yeah, not in the linear sense. Yeah. Okay, where was I? Oh, yeah. So the loss after learning p neurons is exactly this. It's p to the 1 minus 2 beta, so something going to 0 with p. And you just do a simple change of variables, and you'll get this back. Because you know you need it now change from learning the pth neuron to like time. So there's some simple change of variables to do. And similarly, the approximation, this is not the proof, but the reason you get this is very easy. You just check what error using m neurons would get you. The best you can do is m to the 1 minus 2 beta. It took some work, but we eventually proved you do that with SGD. Our original submission to Colt had something worse. It had the square root of this, so it was suboptimal, but we managed to fix it. Yeah. Okay, so the approximation barrier, this is kind of obvious. It's determined just by the size of the learner. If your learner is too small, you're just, you can only learn the m biggest ones. And that's the error if you learn the m biggest ones. And then this term here, this is the scaling with respect to t, which is running time or sample size. And it's determined by number of online SGD steps. So here's a plot, or here's a theoretical plot of what should happen. What that means is like this is like we took d to infinity and we looked at like gradient flow, basically. So and this is what the theoretical plot should happen, is that when you move this way, your width goes up. So you can see the error plateaus at a lower point, because that's the approximation bottleneck. But the slope is the same, right? The slope, m does not affect the exponent on t. And you can see the slope here is all the same in all of these. And then the total slope is this is the width scaling law. You're fitting a curve to like these plateaus. This is when you do it with an experiment in like 1,000 dimensions, I think, and it kind of roughly looks correct. It's like you get a line and then it levels off to a plateau. And we checked the slopes roughly match. The slope is about 0.3. It was set to be 0.3, and this one's pretty close to 0.3. It's not perfect. You can see that the line slopes downwards faster at the end. This is expected in any finite width because the total width is fixed. Like here, the dimension's 1024. The actual width of the teacher is like a few hundred. So then when you get to the end, the error has to drop to 0. So your slope cannot be aligned perfectly. At some point, it has to just go like that. And that's why here the slope curves a little bit at the end. Yeah, so there's the analysis is pretty tight and kind of expected. It agrees well with this simulation. Okay, but we hit a very tricky issue when we were working on this, is that the continuous time, or running it with a constant learning rate we got, the rate we got, just to remind everyone, is this 1 minus 2 beta over beta. Like I said, this is both a running time rate in terms of the convergence rate of gradient descent, or SGD, but also a sample size guarantee. But something very weird happens, is that this does not match the minimax known rate for learning what statisticians call the weak LP ball, which includes the power law distributed signals as a special case. In fact, this rate is better than the better than the minimax rate. For example, in Johnson's book and Donahoe and Johnson's work in the 90s. So you should be very worried now as a theorist. You've proved a rate that's better than the minimax rate, right? That's not a good sign. I mean, it would be great. It would mean like some paper that's famous is wrong, but that's unlikely. So we looked back and we kind of stared more carefully at what happens, and it turns out something very subtle is happening here, is that basically you really should not interpret constant step size SGD or gradient flow as sample complexity, because you cannot discretize this with a constant step size. The way you have the stable step sizes have to be proportional to this A sub p, but A sub p goes to 0. So it means your learning rate has to go to 0. So the only way to use a constant step size is to choose it as a function of p, which is also a function of the loss. So basically, if you actually choose the best learning rate, if saying I have this many samples or steps, I pre-declare it, and I choose a learning rate, and then you go back and plug in the sample complexity, you get the correct thing. You get 1 minus 2 beta over 2 beta. The previous result didn't have this 2 here. So there's no 2 here, basically. So you have to take the square root of the continuous time rate. So it's some nonlinear time transformation. There's no constant learning rate that will ever solve this correctly. And you can't, because it would violate the sample complexity bounds from 30 years ago, roughly. OK, so now if we use the correct learning rate that decreases to 0, that can learn the pth neuron, we'll get the correct exponent. This now matches what's in Johnson's book and what they proved in the early 90s. For what weak LP balls, this is the correct exponent. OK, and there's nothing wrong with this one. This one is correct and optimal. Let me check my time. Yeah, let me say a few words. Let me say a few words about the proof sketch. So basically, whenever you have a bunch of learners and a bunch of teacher neurons, you want to kind of find the permutation to go between the learner and the teacher. It's kind of intuitive. You just have one thing should map to one thing if everything is working correctly. So this iota here, that's the permutation saying like the neuron W iota of p is the neuron that will converge to theta of p. And we have a matrix of overlaps, which is the cosine between theta q and WP, the dot product. And there's 2 phases for this to work out. In the beginning phase, when your W's are all very small, we initialize kind of close to 0. These are approximately decoupled across directions, meaning that the learning for Q not P does not affect the learning of Q equal P. You can sort of just treat it as a bunch of different models with single neurons. So that kind of maps back to those works I mentioned by Max Tegmark, which kind of just pretended there were D different models added together. That's in the initial phase, this happens naturally, somewhat naturally. It's just by virtue of having small initialization. And then once you reach alignment, meaning this iota of p, this one's still 0, but m iota of q and q starts becoming order 1, then the ones that don't match, they stay small. The ones that are order 1 start growing. And then when they start growing, that's when that direction starts hitting its alignment. That's the T sub p, where you start having alignment. And then after you're learned, another important thing is you're automatically deleted from the model. This is by virtue of what square loss would do, or any regression loss really, is like once I've learned the direction, you're removed from the model and the gradients. Like so, when w iota of q is actually equals theta q, it no longer affects the learning dynamics of everything else. So like there's two reasons for decoupling. One is when the neuron stays small, just the loss function of square loss looks like dot product at 0. Just by Taylor series. And the second one is like by when it goes to 1, it doesn't really matter because like if I've learned the direction, it gets deleted. And the middle phase where it does matter is very short because the transition time is very, very sharp. Like I said, we characterize that transition time up to like 1.01 and 0.99. And the reason we need these very small constants is to show that time is very small. Because the time is very small, although in that regime, all the directions interact because it's very small, you can also bound that it doesn't matter. So really 3 reasons why sort of this, although you have a single model and a single labeler or teacher, that the dynamics are almost as if they're kind of decoupled. And then moving from gradient flow to online SGD is sort of more or less standard martingale things with some minor changes, but nothing super interesting. One very interesting thing is that you always are in the unstable regime. We never use a stable learning rate in this entire thing. Because remember, the stable learning rate requires when the A's go to 0, right? So like roughly the Hessian, you can think has eigenvalues like 1 over A1, 1 over A2, up to 1 over A sub D. But 1 over A sub D is like 0 or infinity, so then the step sizes need to be 0. So the Hessian is exploding, so your learning rate needs to go to 0. So we actually always use an unstable learning rate. But what happens is that there's enough decoupling. You're using an unstable learning rate for the bottom directions. Those directions you gave up because your model is too small to learn them, right? Your model is under parameterized. It could not learn those anyways. So although you're unstable for those directions, it doesn't matter. We just need a bound that you don't mess up the other directions. So basically, we always choose a learning rate with in mind, like we will only learn up to the top P neurons. And then we're going to choose a learning rate that's stable for those P. And then it'll be unstable for all the last D minus P neurons.
Just a question about the noise assumption. So then like the fact that the noise is isotropic is essential, right? If the noise is not isotropic.
The X's are isotropic.
Right.
Is that what you mean?
Oh yeah, X.
The X's, yeah.
So if X is not isotropic, like you won't converge, right?
If it's homogeneous, it's still fine, I believe. Imagine the learner neurons are all ReLU, it shouldn't matter because X dot, like the only thing that really matters is that here, let's say X is sigma. And then this one is so this one, so W dot X is this. So I can pull out just square root. So I can, if I always just pull out this constant, the only thing you need in the Hermite expansions of the Benarus argument is this is normal 0, 1. So like the fact that I can pull this out is important.
Oh,
like that's all that his argument really needed, yeah. But if this is not homogeneous, it would be bad. Like remember, I wrote in my learner because I didn't want to use ReLU. I wrote this, but you would have to modify this. I think I haven't checked, but I'm pretty sure it would be this. But this is bad. You need knowledge of the sigma. You need a whiten, yeah. The issue is like the norm is changing, and then it's not norm 1. Yeah, technically. Yeah. Oh yeah.
Student network actually can be any general function
No. My learner is right now is always a two-layer net that's parameterized to be two homogeneous. Can you see this? Sorry. It's not non-parametric at all. It's just some small two-layer net with M. The sigma can be anything. The sigma can be anything, but it's a univariate function. Yeah, there's some conditions on the tails. Oh, I see. I understand your question. It has nothing to do with Holder. What you technically need is the Hermite coefficients need to decay at some rate, so you have concentration. But it's not very important at all. I mean, the Hermite coefficients in decaying imply some smoothness, I believe. But I don't remember the relations. Yeah. Okay. So anyways, where was I? Yeah. So basically, at the end, we're going to set the step size equal to the smallest one we want to learn, and then we'll get a final scaling law with two nicely separated terms, m to some exponent and n to some exponent. This result is tight on the d, the k, the n, and the m, but not tight on the p. Yeah. I already talked about this. Yeah, there's an edge case. My co-author, Denny, has a paper on this. But this one's really an edge case. In the k equals 2, you can only recover subspaces. So it's not like you don't have this directionality recovering. So it's really hard to talk about emergence, I think. And you look at SGD, they have to look at this projection to Stiefel manifold. It's kind of technical. The other question was what Zaid was asking, and which we did think about a lot. It doesn't seem that easy. When X is anisotropic, and the lambda i's have some power law decay. This is a very common model used to study scaling laws in linear regression. They call them source and capacity conditions. But we're not sure how to do that in this without altering the algorithm to this like projected SGD, where you project with respect to the sigma norm. And possibly we want to look at also scaling laws and skill learning when the learning is somewhat hierarchical. Like you first need to learn some subset of skills and then combine those to learn the next level skills. This kind of relates to what I'm talking about in the second part, but let me pause and see if there's any questions before I start. Yeah. So the Michaud work shows that the Michaud work is, how to say what the Michaud work is. The Michaud work is essentially this. You define a loss that's like, I kind of didn't want to go into it. It takes a little bit of time. Theta p minus WP. Let's say let me just choose a random power. And then their total loss is, to me, this is not a learning problem. This is just adding together a bunch of losses. This is not a single architecture. You just took a bunch of separable losses and added them together. And then each of these has different speed. The difference is, to me, this is a single learning task, which exhibits emergence. And once you add together all the components or skills of this single model and single loss, you get the scaling law. And there's no data in this model also, which is, yeah.
Pragmatic takeaway for how I should think about like emergence and transformers differently.
I don't think there's anything. I mean, I'm not sure. It might have been obvious to you already that emergence plus a Riemann integral got you smooth scaling. If you already knew that, I think there's no takeaway here. If that was obvious to you, but it wasn't obvious to me at all.
Yeah, but like in the Michaud work, we could already see that like lots of small things that exhibit spiky.
It's lots of small things, but it's, to me, this is adding together things that are not even related to each other. Right? It's not a single model. It's like saying I add together the loss for A and the loss for B, but there's no reason to look at their cumulative loss. Right? So this is literally, their thing is you take this and then you integrate this, and then each of these has a time, like the time in which, I'll also call it TP. And that's the argument, kind of. Because these are each scalars and they have a closed form. So to me, it's like you're adding together a bunch of things that shouldn't be added together. There's no reason to look at their cumulative sum. Like you can call them skills and give them names and then add them together, but there was no a priori reason. They don't contribute to the loss. They're not even from the same loss or model.
Yeah. I'd have a follow-up, I think.
Yeah. Anything else? Yeah.
I guess this integral form is so shortage.
I think if you're willing to use this thing called elliptic SGD, I think it's very easy to predict. I don't remember the form, but I believe the A, I think the A only enters this one. Like I kind of forget the form, but it's very easy to guess it. You can, if you just look at sort of the result for linear regression, the exponent should be the same. Yeah. The only difference is that this part is different from linear regression. Yeah. Oh yeah. Oh yeah. Sorry.
Hi. Sorry. This might be a fairly trivial question. It's about the images that you presented earlier.
Yeah.
So at the very beginning, yeah. Sorry. Actually, you can stop.
Oh, this one.
Yeah. So we can see on here the sort of cumulative loss. The y-axis is the loss, and that is optimization time. And then it seems like this distribution of the like where the plateaus are is sort of playing a role in the slope of this red cumulative loss function. But when you actually show your results, it looks like it's more so about this sort of accumulation of. Do you see what I mean? That we
Could you say it again?
Sort of tasks, they're distributed on where their plateau is on the y-axis, but that isn't necessarily.
You mean by plateau? You mean
exactly.
This level?
Yeah, exactly. So that isn't actually important in the final cumulative loss function. Like, why do you see the sort of like difference in?
I mean, it's sort of important. I mean, it's how much it costs you to learn versus not learn, right?
Okay.
Like, so it does enter. The height here is exactly this.
It's that.
Yeah.
But then you put a constraint when you actually do this sort of task that they all have the exact same A, because in the next
No,
round,
they don't have the same A. You should think about the A's as, I mean, in the general theorem, the A's can be anything. They just have to sum, square sum to 1. Okay. But in the scaling law example, they're like, just think of p to the minus beta.
Okay.
They're power law distributed.
Okay. But then.
And that's why their integral gets this one.
And then this sort of visualization isn't necessarily parallel to the one that you have next, where you show these.
Yeah, because this is with scaling. Sorry.
Okay.
Yeah, this is with scaling. I only ran these for the beta is all the same in these. That's why they have the same slope, and this is with scaling to get this. Because like this is like with 10, 20, 30, 40, and so forth. Or it's probably doubling actually, but yeah.
Okay.
This is the m, not the n. Yeah, it's the other parameter. This is the, sorry, it's not in this slide. It's this term.
Okay.
Yeah.
Great.
I have very little time, but that's fine. So like I said, it's completely different. Oh, this is work with my students, Zishen, Ishan, and collaborators, or student Alex also, and collaborators at Flatiron and Columbia, and also Danny again. Yeah, so our motivation in this was to start looking at how transformers can do multi-step or multi-hop reasoning. Like, you know, everyone's talking about reasoning now, and we wanted to look into it too from a more theoretical lens. Basically, we're thinking of problems where like you need to be able to compute what happens, like John is in the playground and then Helen is playing with John. Helen picked up the football, where's the football? And you have to be able to trace or hop along some sort of graph. and then finally track that playground is the answer. That's kind of the sort of motivation. And basically, the way we're thinking about it is you have to do a bunch of function compositions. Like you first evaluate who's holding the football, and then who is he with the football, and then finally the location. So basically, our inputs are going to be football, and then the functions we choose to evaluate. So we're going to, and then the transformer needs to learn how to compose together a list of the input and a list of functions, k functions. So sort of abstractly, we'll view this as these sigmas index which functions to compose, and the x is sort of the point at which to evaluate. Okay, and this is almost a task where we'll focus on. I'll talk about the actual task is slightly different. You can compare this to chain of thought. It's slightly different. Here, chain of thought is known to be very, very expressive, but you pay for it in terms of inference costs, and which might be inefficient for very simple things like this multi-function composition. This function composition is, we kind of want to see is, can a single transformer of very small depth do this internally without like using chain of thought or multiple inference calls? And secondly, can you learn this using gradient descent? Yeah.
What do you mean by the functions? What are their properties?
I'll get to that, yeah. Yeah, I'll get to that in like 3 slides, I think. Yeah. Let me talk quickly. The learner, I'll just probably skip this. It's just standard self-attention. The only non-standard thing is you combine the KQ, combine the OV. Every theorist does this. It's a nightmare if you don't. We're going to live with it. And actually, there was prior work with by Daniel, Clayton, and Matus that did show at least there exist transformers. You can construct transformers of log depth to compose together k functions. And the idea is they called it an k-hop induction head, but really it's simple to generalize it to any composing together any k functions. And similarly, there's a similar result by Bingbing and her co-authors on finite state automata. It's kind of the same message, is that you can simulate k steps of an automata with log k depth only. And I'll explain the idea later. The idea is divide and conquer recursion. That's why there's a log. Let me define our task formally. So like I said, our input will be sigma and x. Because I need a learning task to talk about lower bounds, really, is that I'm also going to introduce some latent parameters pi. Think of pi as permutations. Sigma are also permutations. The reason we use permutations is that the input is tabular. It's on 1 to n. And permutations are the bijective functions, or they're one-to-one functions on the space. For technical reasons, we can't handle non-invertible functions. So everything here I'll say is for invertible functions on tabulars, which is just permutations. Yeah. And we introduce some pi's. You can think of them as identity if you don't like them. I need them to talk about lower bounds. For the upper bounds on gradient descent, you can think of them as identity. This is just to make it a function class. OK, so the expressivity result, which is very similar to the prior works I mentioned by Daniel, Clayton, and Matus, is for any choices of pi, you can make a log k plus 1 with embedding dimension. K is the number of functions, n is the size of the universe. That expresses this. The construction is not hard, and it's very close to what they already did. But let me quickly explain the idea. Is the first layer just stores all the pi's in the transformer. The second layer, basically what you're going to do is you're going to try and compose a sigma and a pi to get what I'll call a 2-hop, which is just 2 of these composed. Okay, and then and the recursion idea is that once you can do this at layer L minus 1, then layer L will compose 2 of these. So basically, what this means is you're composing first, you're learning to compose F1 through Fk over 2, and then also k over 2 plus 1 to k. And then once you compose those 2, you compose them again to get the final result of all of them composed. And I'll go into how the attentions are designed in 1 slide. Yeah, here. OK, so the embedding is basically completely tabular. We are not doing anything smart on the embeddings. you're just going to store all of the permutations. This just tells you what element 1 maps to, element 2 maps to. It's just a table to store the permutations. And then in the first layer, the KQ matrix tells you ij will attend to I pi of j. So it's where pi maps you. Then the value matrix, it just applies the sigma. OK. And because that was part of the input. And then at the output, the first layer, you're going to have computed hop 1, which is sigma I composed with pi I. So now we've computed hop 1, and we just compose those two again to get hop 2. And then you compose hop 2 twice to get hop 4, and then get 8. So the induction goes that assume you're at layer L plus 1, and you've computed the composition, which is the hop of 2 to the L minus 1. So then the residual stream of I and j has the result of this. Then the KQ matrix will make ij attend to that quantity. And then finally, the value matrix composes this with this 2 to the L hop. OK, and then at the end, what you'll have is you'll compose 2 of these hops with some offsets here at 2 to the L minus 1 and 2 to the L minus 1. And then it's 2 to the L. And that's the construction given in the previous work with some tiny modifications for our SETI. OK, so this is to say just there exists quite a simple recursive divide and conquer construction of a transformer of log depth that can express function composition. Unfortunately, there's a negative result is that you have no chance of learning this function from samples. The negative result is from the SQ framework, and it needs to be from some framework like SQ because it's there exists already, and you can show generalizations somewhat trivial here. So it has to be from a computational standpoint. SQ just means you get noisy queries. I don't want to get into the formal definition. You can just think you compute approximate gradients using your samples. And they're accurate up to tau. Think of tau as 1 over square root sample size. The lower bound says you need sample size n to the k. So exponential in k with base n. Anyway, this is basically it needs sample size n to the k using SQ. Bad news. But are we screwed? Not quite. I'm going to give you 2 ways to learn this computationally efficiently. The first way is kind of easier to understand using curriculum learning. I take my data and I separate into those that are 1 hop, 2 hop, 4 hop, 8 hop. Hop means the length of the composition. And then I first do gradient descent on the ones that compose only 1 function. Then I do gradient descent on those that compose 2, and then 4, and then 8, and then 16, and so forth. And I do this, there's log k phases on the same architecture. I just always train the same architecture with gradient descent, but just with different types of data. This works with polynomial and n and k samples. This is good news. This is the sample size we were able to prove last month, but we're trying to make it linear in n and k, which I think is true, but I'm not positive yet. So anyway, right now we have some large polynomial in n and k, although I'm pretty sure it should be linear in both. Where was I? Yeah. So basically, you've improved exponential to linear, polynomial with curriculum learning. It shows you that the role of the easy examples give you some intermediate supervision. Without these easy or intermediate supervision, this task is impossible to learn. So what happens in the gradient algorithm is that basically, when you train on 1 hop data, only the first layer really moves. Although you train all the layers, the gradients of all the layers after the first layer are all like 0. So they don't move. And the gradient on the first layer, it learns exactly what you need. Ij will attend to pi of j. So with 1 hop data, learning the first layer is easy, and you can learn the permutations pi. And then kind of you can guess inductively on 2 hop data, you learn the second layer. On 4 hop data, you learn the third layer. On 8 hop data, you learn the 4th layer, and so forth. And it learns the correct attention pattern. OK, but in practice, curriculum learning is not that desirable. You need a way to tell what is easy, what is hard problems. It's not so clear when it's not toy problems. There's also catastrophic forgetting, is that when you're training on the hard data, you might accidentally forget how to learn the easy problems, which happens. In practice, it's much more common to just use data mixtures. You just you just use some data that's easy, some is hard. Like you have some math that's easy, some's hard, and you train on all of it. And then you just hope the gradient descent sorts it out. And so we want to look at a result like that. So it's kind of the same result. The only difference now is we have data from compositions of length 1, 2, 4, 8, up to k. We throw them all in, and we don't tell it, which is hard. You just do batch gradient descent on all of it. And you can still learn in the same sample complexity. Also some polynomial that I think should be linear, but we haven't sorted it out yet. And the intuition is it's implicitly doing curriculum learning. Basically what happens is that, think about the lower bound. The lower bound, SQ lower bound, basically said the gradients were really small. They're the size n to the k. So basically, if you try to learn k-hops, the data that was k-hops gets ignored because their gradient is tiny. It's 1 over n to the 100. Let's say k is 100. But then the data for the 1-hop gradients has size 1, size 1. 2-hop has size 1 over n. 4-hop has size 1 over n squared. So they're stratified. The size of the gradients are stratified by the number of hops. So basically, if you haven't learned L yet, basically the 2L minus 1 compositions, you cannot learn later stages, and their gradients are super, super small, and nothing happens. So implicitly, you're doing curriculum learning. On the first pass over the data set, you're only using really the 1-hop. The ones with bigger, they contribute 0 to the gradient. On the second pass, you learn the 2-hops, and the 1-hops are done. They're already learned, so their gradient 0. The ones 4, 8, 16, and bigger, they're all kind of smallish too, because their gradient is 1 order of magnitude smaller than the 2-hop, and so forth. So implicitly, you're doing curriculum learning. Here's a simulation showing this does happen in practice. We have data that's 1, 2, and 4 hops here. And basically, we plot the loss curves on just directly training on only 4-hop data. It never goes down as predicted by the lower bounds. And then we plot, train on mixtures. And you can see that the green line is the loss computed only on 1-hop. It goes to 0 very quickly. Soon after, the 2-hop data loss will drop to 0 right after. And much longer later, the 4-hop goes to 0. So kind of it does happen that the learning order is also stratified like this. You really do need to learn the easier cases, then learn the hard cases, at least for this data model. Yeah. It only affects this polynomial, basically. Because, like, we're very sloppy, right? Because, like, the mixture weights are, right now we wrote it for uniform, but it won't matter because there's only log k mixtures. So, like, it only will affect logs, if you can see what I'm saying.
Yeah, so that's in practice, the hard data is always rare.
The hard data is also rare, and you may not have this doubling thing, I think. Right here, everything is on a doubling scale, which I'm not sure, like in math, I'm not sure what it means to be twice as hard. Like maybe twice as long, or I'm not sure. Twice as many number of steps or something. Yeah. But for us, it really wouldn't matter because you would just divide this by the number of the proportion of like if this was like 1/10 of this, this would just multiply by 10. I guess 10 is a lot in practice, but for me, it's small. Yeah. Okay, so let me skip this. The lower bound's similar to parity. It's not. So what we want to think about now is how to learn more general compositions when it's not just these tabular functions or bijections or permutations. When your input is, for example, continuous, then the function can have richer structure than just the permutation group, and also more efficient embeddings. Here, our embedding is very boring. We're just using the simplest 1-hot embeddings. Our embedding size is very large. It's linear in k and n. And I think it's a well-known open problem that although you can express with less embedding size, training dynamics get really messed up although there exist architectures. And that's all I have to say. Thank you.
So can you explain again the permutation setting, like the pi function?
Pi is, so pi and sigma are both permutations. Sigma is part of the input, and pi is unknown. Does that answer your question?
What is the intuition behind, like, for example, in the real world?
You can think of sigma as just specifying what functions apply, and the pi is sort of some knowledge, basically. Like, for example, capital city maps to country. Like Tokyo maps to Japan. Like, it could be that. You just have some knowledge that is not specified in part of the input, but it's part of the training data. Like, it's inferable from the training data. Yeah.
Which paper is it?
These are both cold submissions. Yeah.
Your code actually is mapping from, it's the mapping from of the one space into the same space of the same size, right? So the dimension or the embedding space dimension do not increase or decrease. You just mapping from from one space to another space of the same size, right?
You mean this embedding dimension?
Yeah, the embedding.
Yes, this is completely a one-hot tabular embedding. So it's very, like in theory, for expressivity, I think you can take a log of this and you'll be fine. But not for training, no one knows, I think.
Okay.
Yeah. So for expressivity, I think you can get like, it'll be epsilon correct with a log k plus log n.
Okay, thank you.
Yeah.
Thank you so much.
I was wondering how this changes when the initialization of the model changes. So, for instance, if the gradients of the higher order composition or k-fold composition versus a smaller than k-fold composition conflict with each other for certain starting points of the model.
I don't know. Right now, everything is initialized at uniform attention.
So is it
Yeah.
a correct intuition that like basically you will not get gradients for a larger
Correct, yes.
hop problem at all?
Yes.
But what if, but do you have thoughts on like how one would extend it to a setting where there are some gradients and they are not like compliant with the smaller order?
Like the gradients of
Like so
the
let's say you
two hop doesn't really use the one hop exactly. You're saying?
or maybe the initial gradients you get on your model for the two hop are maybe not the ones that will improve the one hop, and so you can probably fit on the wrong. Like your descent direction might be wrong. I guess maybe not possible in this problem, but
In this setting, it's not possible, but I think I understand what you're trying to say. I think in here, it's the only important thing is that the two hop ones or the two and higher ones, their gradient is smaller. That's the only important thing. They can point in any direction they want, but in this setting, they're always going to be smaller because you need to compose together two things to get their gradient. As long as one is wrong, their gradient will be small.
is there a condition on how small it needs to be?
In the theory, yes. They're stratified by orders of 1 over n. Like the first gradient is 1, the next one's 1 over n, the next is 1 over n squared, and so forth. Yeah. But that's probably specific to the the theoretical setting, I think.
Thank you.
Okay, thank you very much.